harmonic motion, right? We introduced simple harmonic motion. I didn't do any calculations or anything, right? Right, and I showed you. Remember what we did last day, Nikolai?
Yes, sir. We started module 2.
What we did in module 2.
We just talked about
simple harmonic motion, right? So we looked at simple harmonic motion and we summarized the whole thing by what? Soraya?
yes, sir.
And what else we was telling you? We had a little summary on what simple harmonic motion is. That's the energy graph. But we had one little expression that summarized the whole thing. So with that E. Right. So for simple harmonic motion, we said that the acceleration of the object was proportional to the displacement, and they both take place in opposite directions. All right. And then we had this little formula, no, that is proportional. A is equal to minus omega squared x. Right? And then energy. What was the energy graph shape like?
Like a bell.
Right? So the potential energy graph, Nikash, was shaped like this. And the kinetic energy was shaped like the other way, right? And then the sum here was what? Right, so that would be the total. Which graph is this again, Nalia? Which graph is this here? And this graph here is the? Oh, good. Right, and the total energy constant, right? Yeah. Remember that? Yes. Throughout the process, yeah, the total energy be constant. Nice. And we said as the particle oscillating like that, its displacement was given by what function? Shivish? As the particle was oscillating like that, its displacement was given by what function? Which function? Yes, quick. Which number? X equal to? Somebody mentioned that. Right, you remember, as the particle oscillated, right? If the particle started here, that was the maximum displacement, right? So it went from maximum displacement to no displacement, back right. So it followed one of the trig functions. Okay? So if it starts at maximum, then it goes to 0. So what's the graph here? Starts at maximum, then goes to 0, then goes back to maximum in the opposite direction, then back to 0, then back to maximum again. What graph is that? Right? So if it starts at maximum, that was the graph. Right? And remember, we know that omega is theta on t. So therefore, theta is omega by t. So this here was the equation for displacement if we start at maximum. Anybody remember how to go to velocity and acceleration? Differentiate, right? So the differential of x is velocity, and the differential of velocity is acceleration. What's the differential of this? Push ups. Oh, you got you. Okay. All right. Sorry, I'm now seeing it. Yeah. But what's the differential of this? What's the differential of this? Minus the differential of cos is sine. Differential of omega t is omega. Right? And you write back x naught and you write back omega t. Right? And differentiate again. What's the differential of sine?
Cos.
Right? Cos. What's the differential of omega? Omega by omega is? So these are the three functions for displacement, velocity, and acceleration. Now, right? If you differentiate cos, you get minus sine. Differential of omega t is omega. And then you write back the x naught. How come you not? As a constant. What's the differential of this? Would you differentiate this? Minus 8 sine 40. Good. That's okay. So differential of this will give you this will give you this. Right? Since we're on the graphs, anybody can help me just sketch some graphs real fast. Can you help me sketch this graph fast?
Starting from the origin.
Cos. So you're starting from x naught and you're coming down here to minus x naught. That's okay? What will this graph look like? Right? But how? Are you going on top or underneath?
Underneath.
So you're starting underneath. Right? The maximum value is minus omega x, sorry, plus omega x naught minus omega x naught. So you all follow how to find velocity. If I ask you to find the maximum velocity, it's this. Right? Omega x naught. That's okay, Arya? And what will this graph look like for acceleration, Arya? Starting to show cos. Very good. Nikolai. It's basically the reflection of this.
Hey. And that's the whole slide, right?
Yeah. Right? So it's basically the reflection of this. Anybody remember what law is, where that came from? Why is this a reflection of this? What's up? What's that, Aaron? What make it so? Why is this a reflection of this? Why is displacement a reflection of acceleration? Huh?
Yeah.
Ask Aaron why it is these graphs looking like that. If I reflect this in the x-axis again, so technically this is the negative of this. Why? Look back at the beginning of the class. Online? Are you okay there? Are you with me there? Right, because it's simple harmonic motion. Because simple harmonic motion says the proportional by in opposite directions. Right? So the proportional by in opposite directions. Are you okay with that? Okay, now? Right? Nalia, you okay with that? Sure. So therefore, this is the summary for simple harmonic motion. I want you to remember that the maximum velocity occurs at maximum amplitude, right? I have one question. In the notes, Zaria, suppose we didn't start at what? Suppose the pendulum didn't start all the way here, but it starts here. What will the function look like? Suppose the pendulum didn't start at maximum displacement, it starts at 0. What will change here? start at maximum, so the graph look like a. If you start at 0, the graph will look like a. The graph will look like this. You start at, think about it, you're starting at 0, then you're going to maximum, then you're coming back to 0 with a sine graph. So the formula looks like this instead. It will look like this if we start from minimum. Therefore, you'll have to differentiate and differentiate. Online, are you okay with that yet? You're okay with how I came up with these relationships and how the graph correspond? Prove what? Yeah, you gotta be able to do those things. Right? But as I told you, people who can't differentiate, you can learn this and then learn the differential in the table in the notes. Right, Saraya? If you can't differentiate, you can learn that. Right? So you can learn these off and learn that one. Please remember that omega is theta on t, and omega is also what? What is omega? Well, yeah, angular velocity or angular frequency. 2 pi? 2 pi. Nice. 2 pi. All right. So make a note of this summary, and today we'll start to do some calculations on it. Go online. Huh? This is true. Amanda, show Amanda this. All right. So let's see if you understand simple harmonic motion analysis, right? You gotta read it. All right, let's start here. Shavish. What's the answer there, Shavish? A, B, C, or D? Huh? Yeah. Which one there is the energy to graph? Shavish? See, why I say C? I kind of looking a little more like A. So, I mean, no. Why you said C? Sitting on the board still, boy. Look at the board. Huh? Look at it. Why is it not D? Right? Because the graph's labeled wrong, right? Potential energy is really where kinetic should be. Okay? So kinetic is maximum at the middle. And potential is minimum at the middle. So the answer is C. Right? Next one, Saraya. Next one is yours. Where?
So no, he can't just.
All right, so what is here? We have a graph of displacement undergoing simple harmonic motion, right? What's the frequency? Look at the function. X is equal to what? Write the general form of it. What is it? Nalia? No, Theta. Nakela, right. Nakela. What's the general formula there for simple harmonic motion? X is equal to what? Displacement, huh? Which one there? Which one? X is equal to? Would it be cos? What's it good? Sine omega t. That's okay? What they ask you for? Frequency. So from the graph, what we can read off, sorry, from the formula, what we can read off? Right, we can read off omega is equal to 0.45. And we can use that to find f, right? How come? Omega is what? 2 pi. Omega is 2 pi. Right? The pi will cancel and 0.4 divided by 2 is 0.2. So the answer is 0.2 hertz. No, write it down. Try and work it over. Right, Nilia, while you're writing that down, Nilia, I want you to tell me what is velocity and acceleration. When you do that, I want to ask you a question after. If I can ask you one time, what is the maximum velocity and what is the maximum acceleration? Right? Sorry? X naught is maximum displacement. My question is, what is maximum velocity based on that? So take that same equation, find velocity for me, and find, after you find velocity, find acceleration. If you don't do it, it'll be a lane. Should we do it too? Every day do it? I want you to tell me what is velocity and what is acceleration. Using the same equation. And after that, what is the max velocity and max acceleration? Just leave that. Right, are you done? Everybody has to do it. What is the velocity? What is the acceleration? And then tell me what's the maximum for each one. So yeah, differentiate, right? Can differentiate, Malia? It was everything. Who's our deal? Who's our runner? She was there all the time. Runner, deal, conclusive. Yeah. Mohammed. Oh, it's up. Next you. Yeah. Yeah, that was right there too. Everything right. Right, so velocity is what? Velocity is 0.4 pi multiplied by 8 cos 0.45 t. Remember that? No, right, doesn't remember that. The differential of sine is cos differential of sine cos, and the differential of 0.4 pi is 0. Sorry? Differential of sine is positive cos. Yeah. Differential cos is minus. Okay? So based on this here, Nilia, what is the maximum velocity? Based on this equation, what's the maximum velocity? Look at this here. What does give you the maximum velocity? And this, which is the same as whatever in front of sign. So the maximum velocity is 0.45 by 8. Okay? Yes. Alina, what's acceleration? Nicola, you might as well say it now. Acceleration is what? Minus 0.45 squared by 8 sine 0.45. Right, remember, the differential of sine cos is minus sine, and the differential of 0.45 t is 0.45. So, Nikita, what is the maximum acceleration? So 0.45 squared multiplied by 8. Are you okay with that? Online? Simple accent, right? Very unusual. Yeah? Yeah. Who ran you? I see Ariane online. Oh, yeah, ran you there. Simple missing.
Yeah, I think you were getting that.
Okay. All right, so that's to show you how to use the differential, right? I think I have one more multiple choice. It's some kind of easy. What's this here? What is this here? What's the answer there? Yeah, what's the answer here? So they said that particle oscillations, a straight line with simple harmonic motion, the period is what? Independent amplitude. That makes sense? How come? How come? Well, we know, and we know omega is equal to 2 pi f. So t is what? Period is what? 1 over f, or, yes, 1 over f, or 2 pi over omega. Okay? So is period dependent on amplitude? Period is dependent on 2 pi, well, sorry, omega. Or period is dependent on frequency. Right? The period is directly proportional to the displacement from the origin. Now, that's it, that's right? Directly proportional to the acceleration. Now, these two proportional. Independent of frequency, definitely not, because it is dependent on frequency. And part T represents the is independent amplitude. Right? There is no amplitude in this relationship. All right? All right. So that's just a quick refresher there on some of the things, right? You'll see that? You see now there? So there we have a body moving with simple harmonic motion. You can see the bar is a kind of faded thick, but I can't remember what year it is. You can see it? All right. Look at the graph. How we know that simple harmonic motion, Shivish? You watch me, I watch you. Tell me now. How we know that is simple harmonic motion? And displacement versus time, right? And displacement following what type of graph? Or what type of graph is that? A sine graph, right? So if it's following, a sine graph, then it follows the graph in top there, right? It follows x is equal to x naught sine omega t. Correct? Yeah? This is part B. Part A is set it with simple harmonic motion, right? Right? So that's one of the ways to know. Now they want you to find the amplitude. Right? Because questions said it here should be. Right? How do we get the amplitude? Let's go back to series. What's the amplitude on the graph? See the graph? Yes. So you can read off the amplitude. 1.5 what? 1.5 centimeter. What is angular velocity? Huh? Right? What is angular velocity at area? Huh? Omega, right? And omega is equal to what? Pardon me? Yeah. Yes, as area. Omega is equal to what? It's not an example, you can look on the board. Omega is equal to on the board. Amelia, what is omega equal to? Angular velocity. Amelia, what you got for omega there? Omega is what? It's only a matter responded. Huh? Well, yeah. But it's also 2 pi on theta. I mean 2 pi on t. Or 2 pi f. Get it? 2 pi frequency. Two pi on t, right? So what is t, Azaria? T is what? That's ms. T is what? For one cycle is 200. You see? Oh, you can't see, Kellen. Right, it is 400. 400 what? Meters per second? Milliseconds, right? 400 by 10 to the minus 3. All right, Amelia, over there, online? You're there still online? Adrian? Ishmael, you're there? You're following? So the formula for omega is 2 pi on t, right? And from the graph, we got 400 milliseconds. What is that? How much is that? How much? 15.7 radians per second, right? Radians per second. Pi. Okay. All right, next one. One for that. Write down an equation for the motion of the body. When you're talking about it, write an equation for motion. And then use it to find the maximum velocity. Write an equation for motion. Gosh. What's the equation for motion? So we already know x is equal to x naught sine omega. That's okay? So write down the equation for the motion. That's the one I cannot give you already. That's okay, Arya? Arya, how we get maximum velocity now? Maximum velocity is always what? Look at the graph, still on the board. What is maximum velocity? Huh? Omega x naught. Very good. Right, so watch here. Maximum velocity is omega x naught. Enough? Right? See that? Look it out, please. Omega x naught. Omega x naught. One point five centimeter. Pava. Captain, what yes? That's a 50. Divide 50. Where is charge? Let's see. Yeah, well, like that. Well, where we got type. Right, so omega is what? Omega was what again? 70 point. How much? 15.7 and x naught is 1.5, which is 0.015. So your maximum velocity, your max. Right. What you all got? What you all got? Let me get multiplied past that. Hey, anybody borrow my Casio and then get my back? Huh? So that's not.
Yeah, so just do it.
No, I have mine in my bag. But I have somebody else who I've taken out. Yeah. I want to send. Oh, Anybody recognize this?
Can I see the chair behind?
That's the regular first class.
Oh, not everything I find. Right here. The answer was? Well, you could get a calculator. Right? I got 0.2355.
Yes, sir.
All right.
You're the first answer.
Never gonna figure out. So you can put 0.23 seconds.
Yes. Say that yes to this paper.
I just have all the questions compiled. All right, so let's take a look at the next one. Right, try this one here, please. Anybody remember what type of oscillation was this one here? Underneath. What type of oscillation was that? This one here. Huh? So what type of oscillation? Yes, simple harmonic motion of F. Starting with F. Huh? Lose any energy here. Huh? Undamped system or a free oscillation, right? A free oscillation.
As we do, after station,
Yeah, no energy loss. Undamped. Try this one here now. Online, it will be nice online if you all can message some answers, right? On this?
Yeah. It's about physics.
Oh yeah, do that fast. I don't know what year it is. That's cool. You know, there's sometimes years out, but it was classic class. Right, we'll go that fast there. Huh? Who don't understand? Which part did you understand? Which part did you understand? So you want to get omega, right? Right. So first thing you have to do is, I don't know. Right, you have to see where you come comparing it to. That equation, it looks like this one or this one. So can you read off omega from there? Right. So you have angular frequency.
Yes. Yeah, you get true. I see on the frequency. Oh shit. Ela ia para o impulso. Meu pai se disse ele não pegar o bar, ele que vai vai. Yeah. Eu ganhei na live para ti. Tiro do comprar o melhor. E não foi para tu. Tiro do comprar o melhor.
Well done. So after you figure out the displacement, you have to figure out the velocity and acceleration. And as I said, if you can't differentiate, I gave you all the rules in the notes, right? All right. So the equation we're comparing this one as Zaria's question. It work around it.
Serious?
Yeah. And you was here at the few months Monday or something. Four. It's in 4-5.
You know, sure.
Yeah, you're up to summarize everything. I'll take it to. Right. So what equation we're going to compare this to? We're going to compare it to x is equal to x naught sine omega t. Right? X is equal to x naught sine omega t. So therefore omega is what? Omega is 3 pi. What do you ask for? Angular frequency, right? So angular frequency is omega. Angular frequency is the same as angular speed, right? Yeah? How we going to get the period now, Shivish? Period is what? Go ahead, you have omega. Confirm your what? I talk in English? Yeah. 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 2 pi, so angular period is 2 pi over omega. So that's 2 pi over 3 pi, which is 2 seconds.
So the answer is always 3 pi?
Angular frequency is also called angular speed. They both the same thing.
Is that one pi?
Where you all did? Find for F?
Yeah.
Look, F is frequency. Are you confused? Liban? Yeah, same as angular speed. What's the same thing? Oh. Sorry. Right, so what's the formula for displacement? X is equal to, right, or 2 by 10 to the minus 3 sine omega, sorry, sine 3 pi t. Right? That's the same formula here. Right? Hurry up. So how do I get the value when t is 1? The different color. Use you see that? So I'm gonna put t as 1 and x is equal to 2 by 10 to the minus 3 sine. Right, we have one problem here. We have to move calculator must be in what? Question. Will the value be more than this or less than this? What? More than or less than that? Less than, right? Because that's the maximum displacement. What you get? 0? Yeah. Because it's 3 pi, right? 3 pi is, right? Sine 3 pi is 0. Sine 3 pi is 0. Right? 1 pi, 2 pi, 3 pi. How we get velocity? Alina. How we get velocity? Differentiate, right? And again, if you can't differentiate, well, you differentiate this different equation. Pardon me? Yeah, it's not out cost. If it starts at maximum, cost. If it starts at minimum, it's sign. If you look at the table in the notes, it has both of them. Who said answers there? Amanda. Very good, thank you, Amanda. Ariane said something. Yeah. Right, velocity. What is velocity? And make it No, the differential of sine cos. So it's what?
2 multiplied by 10 minus 3 divided by
2 by 10 to the 3 multiplied by 3 pi cos 3 pi. And then put t as 1. Zero point 0.19.
Sorry.
0.01. Anybody confused? Anybody confused? Okay, are you confused? Oh, again, acceleration. Okay. Do it fast. Sorry, ma'am. And the minus sign. Any questions online? Ishmael, you're okay? Destiny?
you get 1 part of this question.
Well, you will get error. No error carry forward. Yeah. So you get no error carry forward in ABC. Right, like a little formula on it. Like if you differentiate, right? A substitute wrong, you'll get a mark. Pardon me, ma'am? Which one? That was philosophy. Very French. Acceleration is what? Oh wait, tell me the formula first.
Negative 3 pi squared.
So it's 2 by 10 to the 3 by 3 pi squared, put a negative sign in front, sine 3 pi t, then plug in t as 1. I get a negative for v for acceleration. What is it? A negative for v and 0 for acceleration. Oh, so what's the answer? Negative 0.019?
What's so nine?
Huh?
For you also.
For v.
0.19.
Positive or negative?
Positive.
Okay. And the next one is what?
Negative 0.029.
All right.
So we have
For what?
that on time to this. Is that on time to this?
Let me continue. Ariana, sorry. Ready?
Yes.
Simple again, 0. Check what you will get now. Which is true? Sine 2 pi should be 0. Huh? I don't know. It should be 0. It should be 0. Huh? Let me calculate and see. It's a degree, right? Right. How to be in radians, right? All right, let's go again. State 2 conditions. Hello, after 5 minutes.
Yeah.
After this one. State 2 con. I think I'm missing up. I think there's 2018. State 2 conditions that must be satisfied for simple harmonic motion to a curve. Harriet? Huh? 2 specific conditions set up on the board.
Is that proportional to
So the acceleration proportional to the displacement, right? And they take place in opposite directions, right?
So it's another tree.
Pardon me.
Oh my
But
God.
those are the two main conditions. Huh? I give you all this form.
That is one. We are from the acceleration.
Last one here earlier. Last one here. And I'll give you 5 minutes, right? I'll check back. Sorry? I find kinetic energy. So you need M I need V, so I gave you everything you need. Kinetic energy is a half mv squared. And you have mass. So you had to figure out how to find velocity. I don't know. I don't know anything right now. You do your thing. Gosh, not be real then. Yes. After that 5 minutes. Come on. 6. 3 marks. Right? So we already know that we need kinetic energy, right? We already have mass, so you have to figure out how to get velocity. And I'll just give you one hit. Maximum. Well, right? Yes, okay. What's that? Just enough. Excuse me, who are you thinking about? Aria, you're done. You don't know what to do because what you'll have to find if you have mass, you have to find what? You have to find velocity. So you need to find which velocity. Minimum velocity, zero velocity. Which velocity you have to find? Maximum. And what's the formula for maximum velocity? Well, on the board itself. Maximum velocity. This is the equation for velocity, but what is maximum velocity? See that? Yeah. Maximum velocity is omega x naught. Right? What x naught what x naught Shavish? Shavish, what's x naught? Huh? What's x naught? What do you represent? What does x naught represent? And the factor Shavish, you see what x naught is? Did you write it down? X naught is the amplitude, right? And omega is the what? Angular frequency or angular velocity. Oh yeah, work it out quick. Let's see what you get. So you want to get max velocity, right? From the graph, you see no maximum velocity is. Look at this graph. What's the largest velocity? From this graph. What's the omega extra? So omega is what? How you find omega? 2 pi f. And how you find x naught? X naught is the maximum displacement. So really young question. See that now? So as a really question, you should probably highlight this is frequency, this is x naught, right? So you'll know what quantities you have and what you're working on, right? Yeah. Anybody get up to maximum speed?
Wait. We get 8.5.
Sure, my 0.5 is sure. Did I get something else? I get 0.084.
Yeah.
Oh, that's what I meant. Sorry, yeah.
2.47 by 10 minus.
0.095.
I get 2.087 by. I got 2.087 by 10 to the minus 5. No wrong, you know. Yeah. So 2.09 if you're probably wrong though.
2.1.
No.
Okay. 2.0.
2.0. Am I still confused? Square velocity. 0.85 squared. And it's how much? Zero. 5.8. Hold on, maybe I didn't square. That's not what I mean. Maybe I didn't square.
But nobody from last exit. It's
Wait, again, 7.25 now.
That's like 2.019
That's not.
0.5
0.5 multiplied by 0.0058 multiplied by 0.085 squared. Abacus. Yeah. 2.01 by 10 to the minus 5. Yeah.
Yeah.
Any questions there online? Maybe I'll follow what's on. Right, so some of you all write this down in red, please. Maximum velocity at omega x naught. Maximum velocity at omega x naught. Right, I think some of you all, you're not seeing that, right? Even if you're not seeing it on the graph, just write down maximum velocity at always omega x naught. All right? Are you okay with that? Levi? False? All right?
We have a 5 minutes.
Take a 5 minutes now. Take a small break and then we have an action to do. Anybody confused? Come on, I'll show you over. Online, you're okay there? Take a 5-minute break and then we go and start. And then we go and just look at something else, right? Right, so next thing you want to look at, you want to go back to the handout. And there are some things I want to look at, right? All right, so we went through all these things on the handouts already, right? We went through as an oscillation, how we define simple harmonic as area, the graphs, all these graphs here. We talked about velocity and how to get those little things, right? There's one more thing that we need to work out, right? And we need to be able to figure out how do we determine if I give you a body, how do we determine if the body moves with simple harmonic motion? All right. So you want to figure out how the body moves with simple harmonic motion. All right. So let's just run through these little steps here. So the first thing you do is draw a diagram, right? With the body at an arbitrary displacement x from the origin. On the diagram, mark in all the forces acting on the body and determine the resultant force, right? So the steps again, step 1, draw a diagram, some arbitrary distance x away from the equilibrium. And then continue all the forces acting, and then find the resultant force. Okay? After you do that, then applying Newton's second law, which you hopefully remember, F equals ma. And if you could prove this, then the body has simple harmonic motion, period, 2 pi on omega. That's okay? So we're going to take a look at some examples, right? Got the hand up? Huh? Oh, I didn't send it? Let's give me 1 second. Send it. Yeah, I just sent it back in the group there, right? Everybody get it now? Okay. Go on again. All right, nice. Right, so we're gonna take a look at it. We're gonna take a look at a couple examples, right? So first one, right? We'll do the helical spring. Consider a light helical spring with one end attached to a fixed point on a smooth horizontal table, and the other one attached to an object of mass m. Right? The object is displaced slightly from the equilibrium position through a displacement x. I was saying that there. We have a diagram and we are applying all and we displace it some distance x away. Everybody okay with that? So let's see if we could apply some forces here to it. All right, so when you apply a force here, right, the restoring force, where will the restoring force at? So when you pull it to the right, it will pull the object where? Back to the left. So the restoring force is that way, which is really the what? I use T to kind of help you.
But I don't like to go back inside.
That's really what? Tension. Tension. All right. So therefore, F is equal to minus T. Remember, F is equal to MA. What is tension equal to for spring? T is equal to what?
Length of the spring.
Yeah, T is like tension. Tension equal to what?
Mass.
If it's a base hook law. T is equal to K by extension. Remember this? F is equal to Kx. So the force is the tension. All right. So if I were to substitute here, right, carry across the M, I'll get A is equal to minus KMX. What does that show, Saraya? What does A equal to minus KMX show? It shows that A is proportional to minus X. So it shows simple harmonic motion. So it shows that if I were to displace this, it would oscillate with simple harmonic motion. Right? I'm going to show you back one more time. Right? So I'll give you a diagram and I'll displace it some distance x. Right? If I were to apply a force here, that force will be equal to tension. So F is equal to minus T. F is equal to MA, tension is equal to minus KX. X is the displacement. If I bring across the M here, I'll get A is equal to minus K on M by X. Right? What does that show? That shows that acceleration proportional to minus X, which shows simple harmonic motion. Right? Since the object has simple harmonic motion, this here is equal to omega squared. How come? Look at the formula there. A is equal to minus omega squared x. Okay? So that means that omega is the square root of K on M. Are you okay with that? Just look at everything right there, everything in the note. Omega squared is equal to K on M, and therefore omega is K on M, and period is equal to 2 pi M on T. Anybody use this in the lab? No?
Yeah.
This is module 2? Yeah?
Yes.
So this is the formula for period of a spring moving with simple harmonic motion. All right? You okay with that? So we're going to do the most popular one now, right? You also can read up on this one. The most popular one is the pendulum. All right? I'm going to do it on the board. Pendulum. Right? So we're going to determine if a pendulum moves with simple harmonic motion. Does it? Yes, it does. So it moves with simple harmonic motion, right? And we're going to find the period it moves with. Right? I'm going to do it on board, right? Right, so how do we show now that a simple pendulum is moving with simple harmonic motion? And then from that, you gotta be able to do the proof, right? That's why I'm doing it, right? You gotta be able to do the proof pressure. Yeah. Right? This here is the equilibrium position. When you give it up, that's the equilibrium position. Let's say we take the pendulum and we pull the pendulum away an angle theta, right? Then what's the displacement here? And the displacement is here, x, yeah? And this here is the length of the pendulum, okay? So whenever you have, take a look here, Nalia. All right, so if you look here, this here zero is the diagram for pendulum pulled at distance x away. Okay, so the displacement here is x. Pull the pendulum away at displacement x, we have the length and we have theta. What's the next step? Step number 2 is to apply all the forces. So here we have weight, mg, and well, we have tension if we need it. I don't think it needed here. Are you okay with that? Yeah? And now we go into ion joy diagram. Go ahead. Huh? Trying to show how a simple pendulum moves with simple harmonic motion. Copy down fast, and I want to do the explanation. Yeah, everything. Same shape diagram. I just add x on it. So let's test the diagram before we talk through it. Any notes, sir? All right, so watch it. Everybody watch it. This is the notes, right? So I want you to understand what I'm doing. So step number 1, we need to find F. F is the resultant force, right? What is the resultant force? So what is the restoring force for the pendulum? What's the force pulling this pendulum back here? T? Okay, the tension in this component, right? So T is what in this component here? T is equal to what? Sorry. If I resolve this horizontally, what would I get? T. If I resolve horizontally, won't I get T sine theta? Yeah? Right? And it always, yes? And it always acting back towards center. Even if you pull it away here, it acting towards the center. So F is equal to minus T sine theta. When the system is in equilibrium, right here, tension is equal to weight, right? So when the system in equilibrium, T is equal to mg. So this T value here is really mg. So F is equal to minus mg sine theta. This here is the restoring force, right? And we know the restoring or the resultant F is equal to ma. Correct? F equal to ma. So it means that ma is equal to minus mg sine theta. The m's will cancel and you'll get a is equal to minus g sine theta. Right, but here's a little complication, right? Those who did limits will see it. Theta is very small. So when theta is very small, this sine theta value is approximately theta. So if theta is a really, really small angle, then sine theta approximates theta. Right? If you try to make a calculator, find sine of 0.00005 and you will get back 0.0005. Right? So sine of a very, very small angle is that small angle. Right? That's limits, right? Right? So this formula now becomes A is equal to minus G sine, I'm taking off sine theta. A is equal to minus G theta. Does this show simple harmonic motion? No. So we gotta bring in X somehow. If you look at the graph here, if you look at the triangle here, what do we know? We know that sine theta is equal to, yeah, you can use that too. Sine theta is equal to opposite over hypotenuse. That's okay? Right? I care what. Let me leave out this in case some people then do limits, because you could also do the same thing here. From this triangle, you're seeing sine theta is equal to what? So sine theta is x on L. You end up with the same thing. So again, A is equal to minus G x on L. Correct? Does this show simple harmonic motion, Shibish? Does this show simple harmonic motion? Yes, because A is proportional to, and omega squared is what? No, omega squared is just this alone. Omega squared is G on L. So omega is the square root of G on L. And we know that period is what? 2 pi on omega. So period will be 2 pi all over the square root of G on L. And if you flip it up, you'll get T by 2 pi square root of L on G. I'll show you what that turns my lab between form 5 and now. Yes, right? So this is the period of something moving with simple harmonic motion. Okay? Yeah, you have to realize. Plot the graph of 1 on L, T by root L, T squared or something. Okay? So this is how you show that a pendulum moving with simple harmonic motion. Right? So you gotta be able to prove this. Right? Our next version of this proof is this, right? I didn't want to complicate it too much here, but here what you could also do. You could resolve mg, right? And you can resolve it like this. Right? If you resolve mg parallel to this and perpendicular, you would get this as the restoring force, which is mg sine theta. Sorry, mg sine theta. Right? There's a next way to do it. If you resolve mg, if you resolve it horizontally, you'll end up with mg sine theta. Please remember to include the negative sign because it always acts back towards the equilibrium. Okay? So a next way you can do it is I resolving this, right?
So we could use like magnetic issue, man.
Huh? If you can use this, yeah. All these are proofs. So if a question says find the period during simple harmonic motion of pendulum and you have the length, you could use this. Right? That's what I'm gonna show you next week. Right? I'll go and give it our next week. So remember, we can only use this formula if the object is moving with, right? If the object moves in a circle, we can use period as what? We're moving in a circle. Period is 2 pi on omega, which is angular velocity. Okay? So please remember which formula you're using, right? All right, next day.
Yes.
Well, I think we can do some more now.
Yeah, use some more.
All right. So next day, let's just finish out this part here. All right, so everything here in the note, I want to talk about one more thing I've done, right? We talked about kinetic energy and potential energy changes, and this is to show the simple pendulum, right? Forget that, right? Watch this here. You remember we were able to show using this simulation that the total kinetic energy and potential energy, they are always constant. You got to remember we showed this or we looked at this for object with a pre-oscillation. Yeah. Well, we could also prove it using a formula. Watch this here. So kinetic plus potential is the total energy, right? If you look here, potential energy, which also the strain energy, is equal to half kx squared. Remember that from module 3? Yeah. Potential energy or strain energy is a half kx squared. But remember, we just proved that omega squared k on m. So it means that k is m omega squared, or potential energy is a half m omega squared x. Right? And all this time. Just take a look at it, right? So that is the formula for potential energy. Now, I can find kinetic energy by using a half mv squared, and I'm using this formula here for velocity. I square it up, I'll end up with this. Now, if I were to add kinetic energy and potential energy, you'll recognize that this will cancel off here, and you'll be left with this. Sorry, I cancel off the wrong thing. This will cancel off with this. This should be x naught. All right, so when you add it up, here's what you will end up with. You will end up with a half m omega squared x naught squared. What does that formula show? That formula shows that mass is constant and mass are all the same, right? Omega squared is constant and your amplitude is also constant. So if everything there is constant, then what you will get? A constant. All right? So Nikash, if you didn't follow anything I say, right, because it was on your phone, all I want you to understand is this. Total energy is given by this, where every single one of these quantities is a constant. Okay? You go back on your phone now. Right? So the objective was really to show that the total energy is all constant. All right, so now Next week now, we're gonna mess up this constant energy by damping the oscillation. Right? So we have little damping, we have critical and so on, right? So next week we'll do damping and resonance and finish up